Hi, I'm David Simcha. This talk is on D-specific design patterns. So you guys are probably all familiar already with general object-oriented design patterns in languages like Java and Smalltalk. So the focus of this talk is going to be kind of in a similar vein, but on design patterns that are at least somewhat specific to D. So first of all, why would we study something like this? Well, basically for the same reason we'd study design patterns in any other language. So according to Alan Perlis, a language that doesn't affect your way of thinking about programming is not worth knowing. And one of the more obvious ways that a language can affect your way of thinking about programming is by changing the way you design your code based on the abstractions it offers and the paradigms it offers. So D is unusual in that it combines paradigms in a pretty eclectic way. It's not a researchy language. It doesn't invent a lot of new paradigms, but it does borrow paradigms from a lot of different places. And these new combinations tend to get used pretty creatively in D. And it's nice to be able to give some of these new design patterns names because it gives us a common currency to talk about them. It makes them easier to think about. And the last good reason for a talk like this to give all these patterns names is that given D's metaprogramming capability that has been extensively discussed at this conference, some of them might be automated in a std.patterns Phobos module so that we can stop writing boilerplate to implement them. So I'm going to give a brief rundown. A lot of this stuff has been gone through already of the key features that enable the design patterns I'm going to discuss today. This is mostly going to be a review for those of you who have used D more extensively, but it's going to be important for those of you who are coming from a C++ background and attended this conference more because you're curious about D than because you're already a big-time user of it. So one of the more important ones is just auto, so that's just type propagation. So the compiler already knows what type something is. You want to create a variable based on that type, so auto will automatically infer that type. Static if has also been discussed extensively. I feel like this would have been a better slide to have on the first day of the conference. But yeah, so static if is just conditional compilation based on anything that's known at compile time. And the key difference between static if and C++ style if-def is that static if can use any value that's known at compile time, even if it's computed via templates or compile time function evaluation. Then, along with static if in terms of metaprogramming capabilities, this one I think actually hasn't been mentioned yet this weekend, is template alias parameters. So in C++, you can pass an integer or a type to a template. In D, you can also do strings. I think you can do floating point numbers. And we also have the most interesting thing you can pass is an alias. So an alias is just passing any symbol to a template. The symbol can be a function, another template, for example. We also have Variadic templates, which are also in C++11, which enable passing any number of arguments to a template. Compile time function evaluation. Let's give Don another thanks for improving this feature to the point where it's actually usable. The goal here is that any function that does not affect global state and does not call into code that the compiler doesn't have the source for example, inline assembly or functions that are only available in binary form, should eventually be able to be executed at compile time. So in D terminology, for those of you who are familiar with it, anything that's weakly pure and that the compiler has the source code for. And that has become much closer recently to becoming a reality. Compile time introspection. In D, it's become very easy to look up the type of something if you have a variable and you want to get its type programmatically, or you want to get a list of all the members a class has, or etc. This one hasn't been discussed this weekend. In D, all global and static variables are implicitly thread local unless they're explicitly declared thread global. That's going to show up in one of the design patterns I'm going to discuss today. So if you declare a static variable, by default it's thread local. So by default it's not a problem with regard to threading. If you really need traditional C-style globals, you can add an extra keyword and make it global. And then we have template and string mixins, which allow mixing arbitrary code into a scope kind of like C macros, but more powerful in ways that I'm going to get into later in this talk. So what are the criteria for a D-specific design pattern? Well, obviously it has to be reasonably unique to D, or it wouldn't be D-specific. I'm not going to set the bar too high for that, because if I set the bar too high, there would be nothing left to talk about. I mean, we all program in Turing-complete languages. C++11 has borrowed a lot of good features from D, and probably even more so from the two main minds behind both D and C++, Walter and Andre. So, but we don't want something that you can implement easily in just about any other language. It has to solve a general class of problems, because if it didn't, it would be a design, not a design pattern. And it has to involve minimal boilerplate, mostly because I can't fit anything on these slides that has too much boilerplate, and because it's not very memorable with most of its boilerplate. So the first design pattern I'm going to discuss today is the instantiator function pattern. This is one of the simplest patterns, but it's one of the most important, and it's necessary to understanding some of the other design patterns that I'm going to discuss today, because I show instantiator functions in them. So this one can also be done in C++11 actually, now that it has the auto keyword, and it's incredibly useful for cutting down on boilerplate. So here's an example without the instantiator function pattern. This struct tuple is a highly simplified version of what's in standard.typecons. So it's just a struct template that takes a set of types and holds those types in args. Now the way we instantiate this template, if let's say we have an int, a double, and a string. So we can instantiate the template with an int, a double, and a string, and then pass these three arguments as a struct literal to tuple, and we've instantiated our struct. The problem with this is that the compiler already knows that 1 is an int, 3.14 is a double, and foo is a string. Yet we're specifying that information redundantly. This is really ugly. It's a lot of boilerplate. It makes your code more brittle. If you want to change one of the arguments, you have to change things in 2 different places. And we don't like to type that much, because D people have lazy fingers. So what's the alternative to this mess? The alternative is to declare an instantiator function for tuple. So again, this is a simplified version of what's in standard.typecons. We have our tuple struct again. Now that thing in the middle with the red comment that says instantiator function above it is an instantiator function. So what it does is it takes a set of arguments, a variadic set of arguments, and it instantiates tuple based on those arguments. So the return type is tuple instantiated with args. In D, you can introspect the return type using type of return, so we don't even need to duplicate naming the return type there. And we pass the arguments into the tuple. Then we can go down to main. We call lowercase tuple the instantiator function with an int, a double, and a string. It calls the instantiator function, which automatically instantiates the struct with the right types. And we avoid explicitly specifying types that the compiler already knows. This pattern is used everywhere in Phobos. Pretty much every range in standard.range uses the instantiator function pattern to avoid this horrible typing.
Sorry, I think C++14 has a way to make instantiator. Repeat. I think C++14 has an even better solution where they remove the need for the instantiator function, and they would construct the struct directly.
There's a C++14 now?
Well, it's a planned feature. Where
okay.
you get rid of the instantiator function, it would deduct the type from the input arguments and construct that type.
That's interesting. I wasn't aware of that, although I do know that C++ x+1 features, where x is the current year, tend not to actually pan out in practice. Look at static if. But yeah, that would be useful. Okay, so this is the instantiator function pattern. And it's one of the simplest ones, but it's one of the most important ones. So the next pattern I'm going to discuss is what's known as the compile time command pattern. So you guys are probably all familiar with the Java-style command pattern, where you create a class, it holds a function and the arguments to the function, and then it has an invoke method that automates calling a predetermined function with predetermined arguments at a later time. But it has a set of problems associated with it. One is variadic argument lists. Unless you want to rely on boxing, you're going to have a mess on your hands in languages like Java. Another is that the invoke function, the invoke method can't be inline because, well, for the most part, it can't be inline because it's virtual. Maybe in a super smart JIT it would be, but you don't necessarily want to rely on that. A third problem is return type polymorphism is difficult to deal with in the old school command pattern. You know, figuring out where to store the return type and how to deal with it. In template-heavy languages like C++ and D, you might want to be able to pass an uninstantiated template to a command pattern object. This is important if you don't want to have to explicitly instantiate the template and deal with all the boilerplate that entails. So, you know, you can't pass a pointer to an uninstantiated template. It has to be a compile time construct if you want to do that. And we want to be able to create command pattern objects with minimal boilerplate. So this pattern is actually used in standard.parallelism to automate creating these command pattern objects that are used for task parallelism and standard.parallelism. So the solution to this dilemma of wanting to create a command pattern object without the downsides that Java-style command pattern objects have is to use template alias parameters in variadic templates. So we have our command pattern struct, and it takes as its template arguments an alias for the function. So remember, an alias can be any compile time symbol, including an uninstantiated template. And then it takes a set of arguments as a variadic. Now, its invoked function is not virtual because you can't have virtual functions and structs in D. So it's inlineable, and it simply forwards to the function that's passed in at compile time as an alias with the arguments. Now, since everything is bound at compile time, invoke is inlineable, and the function it forwards to is inlineable, so there should be zero overhead here. Now, of course, we have an instantiator function for this because nobody wants to type out to explicitly specify all the arguments when instantiating the command object. And as a simple example here, we pass in a lambda function that just multiplies two numbers together as an alias. This is actually a template literal because we don't specify the types of A and B. So we're passing an uninstantiated template as an alias. And we pass as arguments 3 and 2. So this object gets created. And then when we call the invoke method, of course we get 6 because at least last time I checked, 3 times 2 equals 6. Anyone want to double check that for me? So this is the compile time command pattern. So this next one is one of the most interesting ones about D in that you'd think you could do it in a lot of other languages, but it doesn't work in practice for subtle reasons I'm going to get into later. And it's one of the most useful ones, so I'm going to spend more time on it than the last two patterns. I call it the higher order range pattern. So the problem here that this is intended to solve is that we have a range that we need to pre-process before passing it to a function or an object. Or maybe we just want to simplify our code by abstracting away some details of how we're processing our range. And we wanted to have O1 auxiliary memory usage. This is especially important for infinite ranges because unlike what theoretical computer science says, we're not running on real Turing machines. We don't have infinite memory. We want O1 pre-processing time. Again, especially important for infinite ranges. And we want minimal wasted effort if only part of the range is consumed. So let's say we only look at like the first n elements until we find one that has a value that we're looking for. So for example, find function. Well, we don't want to pre-process the whole range ahead of time because that would be a colossal waste of time. So here's an example of the higher order range pattern. We process the range lazily. This is a simplified version of standard.range.retro. And what this does is it provides a reversed view of a range. So you have a range that you iterate through in one order. You pass it to retro. Retro makes it look like it has the same elements in the opposite order. So it has a front function that forwards to back. And of course, this is a nice simple function that can be easily inlined by the compiler to have zero overhead. This auto-ref thing here I don't think has been discussed yet at this conference, and it's a pretty important feature. So auto-ref makes it simple to forward return types around between functions. So when you have an auto-ref return type and you return a value, it returns by ref if if and only if what it's returning can be returned by ref, meaning that it's an L value and it's not a stack variable. So of course, forwards to front. Empty, well, your range is just as empty whether you're iterating forward or backwards. Pop front pops the back of the range. Pop back pops the front of the range. And we have to store the range. So here's an example of using this. We have, of course, an instantiator function. This time we do the instantiator function the opposite way. We specify the return type explicitly in the body and return auto, because D allows automatic inference of return types. And so we create an array of numbers from 1 to 5. We pass it to retro, and we test using standard.algorithm.equal, which tests element by element equality of ranges, that it's equivalent to 5, 4, 3, 2, 1, the range in reverse. Now, for those of you from a C++ background, we're storing the range in here, which is an array. Arrays in D are not like arrays in C++. They don't own their own storage. Arrays in D are fat pointers, meaning a pointer and the size t, to memory owned by the garbage collector. So when you pass an array around in D by value, you're actually only passing this fat pointer. So 16 bytes on a 64-bit architecture, 8 bytes on a 32-bit architecture. So we don't need to worry about passing by reference to these ranges or anything. We don't need to worry about what happens if we pass this range around the retro range and the array goes out of scope. So as you can see, garbage collection makes this a much simpler and more transparent way of doing things in D than it would be in C++, among other things that I'm going to get into later. So here's a list of examples or a partial list of the most important higher order ranges in Phobos. So I'm just going to briefly discuss these so that you can see how widespread and how powerful this pattern is. Retro, I already discussed, it iterates through a range backwards. Index takes a source range and a list of indices and iterates over the source range in the order specified by indices. So for example, you can have an unsorted range as your source range and a list of indices as your index range, and you can iterate over your range in sorted order without the code that's iterating over the range having to be aware of the extra layer of indirection. We have take, which takes the first n elements of a range and is smart enough to alias itself away if the range supports slicing. So if you have a built-in array and you do take your array comma n, then what take will do is it'll alias itself away. Take instantiated with a built-in array is just aliases itself to a built-in array. Just slice the array to the first n, return the slice with 0 overhead. The whole thing will probably get inlined. It's probably will generate exactly the same assembly code as just slicing the array yourself, but it's generic. We have stride, which takes a range and iterates over every nth element. So for example, the 0th element, the 2nd, 4th, 6th, etc., skipping the even elements if you do a stride by a factor of 2. Cycle takes a range and a finite range and iterates over it again and again as an infinite range. So for example, if you have an array 1, 2, 3, you would have an infinite range of 1, 2, 3, 1, 2, 3, 1, 2, 3. We have zip. This is one of the more interesting ones in that it can be used to sort multiple ranges in lockstep. It takes a set of n ranges and returns a range of tuples of corresponding elements in these ranges. And then we have map and filter, which should be familiar. Did you have a question?
It should be noted that these are sort of a mainstay of many other languages and libraries and frameworks. But what makes these particular artifacts more interesting is that, for example, indexed offers random access. So it behaves pretty much like an array. And map actually can be random access if its input was random access. So they exhibit just the same, the maximum power that could be imparted by the input range. And that's what makes them so much more useful than sort of the run-of-the-mill, we know how to do take, we know how to do map, filter, no problem.
Right. That's a very good point. I was actually going to make that on the next slide, but you probably made it better than I was going to. And I probably should have made it earlier, too, on second thought. So map and filter are probably familiar to people from functional programming background. Map takes takes a range and a lambda function and applies the lambda function lazily to every element in the range. Filter takes a range and returns a range that iterates only over the elements that satisfy some pre-specified predicate. So this is obviously a very popular and very useful pattern in D. Why hasn't it caught on in other languages? Well, here are some of the reasons. One, to get decent performance out of this, you got to have inlineability of all these little functions that are just forwarding to their source range. So that pretty much it rules out using virtual functions to implement this, which means you've got to use templates. So that leaves two major languages on the face of the planet, plus maybe a few obscure ones like Eiffel and Ada. So we've got D and C++ left. And then, as Andre alluded to, the metaprogramming and compile time introspection features of D make it so that we can make these higher order ranges much more powerful than they would otherwise be. So static if statements are a huge win for this. They're used everywhere in implementing higher order ranges in Phobos. So they make it easier to distinguish. We can distinguish between input, forward, bidirectional, and random access ranges. And in our higher order range, we can offer whatever we can support based on what our source range offers. So for example, as Andre alluded to, map is a random access range if and only if its source range is random access. If not, then it goes down to the lowest common denominator, whatever the source range supports. Type of is incredibly useful for introspecting the type of function. It's equivalent to C++'s decal type, so apparently the C++ people have learned the value of type of and think it's worthwhile for their language too. Auto and auto-ref, as I alluded to. Auto-ref is incredibly useful. Those of you who are fairly new to D, you really don't want to know what standard.range looked like around 2009 before we had auto-ref, when it was basically filled with mixins trying to simulate the behavior of auto-ref. I hope I'm not bringing back too many traumatic memories, Andre. And variadic templates, which are useful, for example, for implementing chain, which is a range that I forgot to mention on my previous slide. So chain takes n greater than 1 ranges. Actually, I think if you give it 1 range, it aliases itself away, which is rather efficient, and changes them together to make it look like it's a single range. Now, of course, this requires variadic template supports if you want to handle the general case of n greater than 2. What's up, Andre?
A sort of a subtle point about chain. So chain, if all of its inputs are random access, does offer random access, which is counterintuitive because you don't know exactly. I mean, there's a blow up, right, in time there that you need to spend. And the underlying idea there is that it's a constant compile time blow up depending on how many parameters you pass to chain. That's not a runtime variable parameter. So if you pass 5 ranges, random access in chain is going to take up to 5 steps to find the appropriate index, but it's a constant time kind of blow up, not a ON blow up.
Right. Okay, so the next pattern I want to discuss is what I call mixin macros. So we've already seen the power of mixins in D, but one thing that I think has been underemphasized to this point is the ability to perform computations on the strings before you mix them in. That's what separates D mixins, or one of the big things that separates D mixins from C macros that are used to implement mixin-like behavior. So a key thing to emphasize is that the entire D operator overloading system is based on these mixin macros. So basically what they help us achieve is, imagine you want to factor out things that are very similar but have minor differences. You want it to avoid code duplication. And you want the ability to use templates and compile time function evaluation to help you factor this stuff out. And since, for whatever reason, programmers tend not to like it, we want to avoid Lispy syntax. So this is a pretty simple pattern. I only have a 1-slide demo of it. This is an example using D's operator overloading and basically mixin macros. So the way D's operator overloading works, for those of you who aren't familiar with it, this is D2's new operator overloading. By the way, it came out, if I recall correctly, at the beginning of 2010, is there's only one function you overload that supports all the binary operators, as opposed to C++ where you have like op star, op slash, op plus, op minus, etc. And it takes a string that represents its operation as a template parameter. So if this is the addition operator, it'll be op binary instantiated with a plus sign. If it's the division operator, it'll be op binary instantiated with the slash sign. And the beauty of this is that instead of writing boilerplate, if we basically just want to forward all these operations to a member, we can write one Mixin macro that automatically takes care of all that forwarding. So this struct is a user-defined integer type. In its current form, it doesn't add any value over the built-in integer types, but you could make it add value by, for example, doing overflow checking. But just for the sake of simplicity, I wanted to not make it add any value. So we want to overload the plus and minus operators. So what do? There should probably be a constraint on this template checking that we either have a plus or minus operator. I kind of neglected that. But so we write an op binary function, and we want to compute the new value for the return value. So we mix in a string for the value of our current LHS, and then we append the operator to it. Remember, the operator is a compile time string literal. It's a template parameter. It's known at compile time. And we append our HS.value, and then we mix that in. So when we mix it in, it's evaluated in the current scope as regular code. It's basically like compile time eval. And the thing I want to emphasize about this is that it doesn't have all the pitfalls of runtime eval. It doesn't cost you anything in performance. This factors at the object file level. This is two different instantiations of op binary. It's just like regular template instantiation, even though the template argument is a string, not a type. And unless someone's hacking your build system, there's no security risk because it's all done at compile time. So if we want to subtract 5 from 2, we created a user-defined int with 2. Subtract 5 from it. That calls op binary instantiated with a minus sign. The minus sign gets mixed in for op here, and it comes out to -3. If we want to do it with a plus sign, at the source level, the same code gets called for addition. Op binary gets instantiated with a plus sign. The plus sign gets mixed in for op on this line of code. And we've got addition, all supported by the same source level code. No crazy boilerplate overloading all the different arithmetic operators manually. And we've used compile time computations to basically create macros. So the next pattern I want to discuss, this is one of the less D-specific patterns, but it's also one of the more useful ones. And the reason I considered this D-specific is because D makes thread local storage a first-class citizen of the language. Remember, static and global variables are thread local unless explicitly declared not thread local. So you guys are probably all familiar with the Java-style singleton or C++ style singleton pattern, where you have a class, you only want there to be one globally available instance of it, and you want it to be lazily instantiated. And you probably all know that this is a threading nightmare, because there's an obvious concurrency problem in terms of making sure that it was instantiated before obtaining it, because it's globally available. It's not available per thread. And we probably want this globally available feature. We probably don't want one instance per thread in a lot of cases. So we want thread safety. We want laziness in a lot of cases because we don't want resources consumed for something we were never going to use. If we were satisfied with eager instantiation, our problems with thread safety would pretty much be solved. We want minimal overhead, so entering a synchronized block every time we want to get our instance is a non-starter because that's a nightmare in terms of performance. And we don't want subtle memory model dependencies. We don't want to have to all be language lawyers. We don't want to have to know what obscure guarantees our language makes in terms of memory ordering. We don't want to have to read the same paragraph 5 times to understand exactly what the volatile keyword does. We don't want to use double-check blocking, even if it works in some versions of Java, if you use the volatile keyword exactly right. We just don't want to deal with that because it's too error-prone. So what's the alternative, given that thread local storage is efficiently implemented within the compiler, not in a library where it tends to be less efficient, as a first-class member of our language? Well, this is the solution that served me well for the default thread pool in standard.parallelism. It's the thread local storage-based low-lock singleton. So we have a singleton class. It obviously has a private constructor. And it has a Boolean variable, a static Boolean variable, that determines whether the current thread knows that this class has been instantiated already. So remember, this is a static variable, so it's implicitly thread local. Then we have a shared, the gshared keyword gives you classic C-style globals, instance of this class. So how do we turn this into a singleton that barely requires any locking? Well, the instantiated variable starts out as false in each thread. That's the default. When you call get, it checks to see if its thread local instantiated variable is true. If it is, then this current thread is already guaranteed to know that this class has already been instantiated and simply returns the instance. If not, we're not doing any crazy double check locking. We always take a synchronized block. We check directly whether the instance has been instantiated or whether it's still null inside a synchronized block, so this is thread safe. If not, we instantiate it and no matter what, once we get to the bottom of this block, we know that we've been instantiated, and we set our instantiated flag to true. So we know that this synchronized block will never be executed more than once per thread. All but one time per thread, we'll just be checking this thread local instantiated variable, and it'll be true. If we access this function enough times, it'll become a predictable branch. It'll cost basically nothing. And so we're having our cake and eating it too here. We've got performance, I'm going to show on the next slide, comparable to thread unsafe. Walter?
I've been hearing about the double check locking bug in this for years and years and years and years.
This is not double check locking.
I know, it avoids that, and it's very clever. And I'm wondering, where did this idea come from? How come I've
wondered the same thing. I actually invented it and then found out that it had been independently invented in a few places, but I was amazed that it had never really caught on as a pattern. That's why I presented it here, even though it's not that D-specific.
I'm really glad you're presenting this one. This is awesome.
Yeah, it's using standard.parallelism too. Andre?
Obviously, it's not this specific, but what I think didn't make it as popular as it could have been in other languages is that essentially it's difficult to create thread local storage in other languages. It's just annoying.
Right, that's why I consider it D-specific enough for this presentation, is because we treat thread local storage as a first-class member of the language, so it's a lot easier to work with. It's probably more efficient because it's implemented at the compiler level. So yes, technically you could do this in other languages, but it's a lot more awkward and possibly less efficient. So here are some benchmarks of this pattern. So we have a thread unsafe singleton on the left, and I benchmarked this with both GDC and DMD because GDC seems to optimize thread local storage better than DMD. And so the y-axis is execution time in milliseconds for 1 billion calls to get. So in the middle, we have our thread local storage-based singleton. We can see there's no discernible overhead compared to the unsafe singleton for GDC. For DMD, there's a little bit, but look at this. It pales in comparison to the naive taking a synchronized block every time. So we are basically having our cake and eating it too. Thread-safe singletons that are almost as fast as thread unsafe singletons, and we still get lazy instantiation. Question?
So unsafe is the double-checked locking one, or is it no locking at all? What's the unsafe implementation?
Thread unsafe is just what you would do if you knew your program was single-threaded.
I see.
It doesn't deal with the concurrency issue at all. It would be horribly broken on multi-thread code.
If I could suggest, Google double-check locking bug. It's not something that's simple to understand. It took me like a week to figure out what the problem was, and it's been bedeviling programmers and causing weird problems for years and years and years and years. So yeah, Google it, and David up here's got a solution to it. It's just awesome.
And Walter, actually, I remember a forum post where Walter basically taught me about why double check locking is broken back in like 2008. Okay, so the last pattern I'm going to discuss today is semi-automated loop unrolling. So loop unrolling is still a useful optimization in some cases nowadays, even on modern CPUs with pipelining and good branch predictors and everything. If it breaks dependency chains, especially dependency chains that the compiler is not even in principle allowed to break because of the way floating point works. So this is an example of an unrolled loop to compute a sum. We have it's two-way unrolled. We have two accumulator variables, sum 0 and sum 1, and we iterate over them in blocks of 2. Of course, I'm not dealing with the stragglers if we have an odd number of elements because it's kind of extraneous to the point of this code. But obviously, in a production implementation, you need to. And we add every even element to sum 0, every odd element to sum 1. What this achieves over a naive implementation of the sum function, and I'm going to show benchmarks of this in a few slides after I get done describing this pattern, is it breaks every other dependency chain. So these are two independent instructions that can be executed in parallel on a modern CPU core that has instruction level parallelism circuitry. But there are two problems with this. One, it's a pain to modify the unrolling factor. You'd have to change stuff here. You'd have to copy and paste this line here. You'd have to add more sum variables here. It would just be a mess. You certainly wouldn't be able to do it without having access to the function body, which matters in some cases. And the other is, imagine if we're computing something more complicated than a plain vanilla summation. Imagine if we're computing a dot product or Euclidean distance or something like that. Then we'd have a pile of code duplication in here. I guess you could factor that out with a lambda function, but it's still not that pretty. So what do we do instead? Well, D tuples are automatically unrolled by the compiler. So we create a tuple of the numbers 0, 1, 2, and 3. This is for four-way unrolling. It actually is possible to create a static iota function where we pass static iota instantiated with 4, creates a tuple from 0 through 3. We don't have that in Phobos yet. There was a long forum discussion on that a long time ago that I don't remember the details of. So we create our endpointer. We create a static array of accumulator variables. So remember, a static array is allocated directly on the stack. If you have a compile time offsets from a static array, it's at a known offset from the stack pointer. So it should have 0 overhead compared to regular stack variables to access a static array. And so this outer loop iterates over our array in blocks of 4. This inner loop is automatically unrolled by the compiler because it's a loop over a tuple. So basically we have this translates to sums bracket 0 plus equals p bracket 0, sums bracket 1 plus equals p bracket 1. So again, these offsets are known at compile time, which enables some optimizations in terms of being at a fixed offset from the stack pointer. And then at the end we sum up our accumulator variables and return into the first one, and we return the first accumulator variable. Now the beauty of this is that if we factored this tuple out into a static iota call, so remember static iota is a hypothetical template where it creates static iota instantiated with n, creates a tuple of all the integers 0 through n. If we factored that out into a static iota call and made the unrolling factor a template parameter, we could vary the unrolling factor without changing the body of the function. So, Andre?
That shouldn't be hard. You can just pass the limit into sum and then do the static iota trick.
Right. It's it wouldn't be difficult. I just didn't.
Right.
It's just that we don't already have static IOTA in Phobos, and I didn't feel like writing a static IOTA implementation up here for this demo.
I have a question though. So I see you for every step you sum to all like 4 slots. You have
Yeah.
like these 4 slots statically allocated. Traditionally, people kind of add, create 4 variables and then they add all 4 together at each big iteration in the loop. Why did you approach things this way?
I'm not sure I understand the question.
We can take it offline.
Okay. So here's an interesting benchmark. To demonstrate the value of this, I made a benchmark of the sum function. I don't remember exactly how many iterations of it and how many elements I was summing, but this is a sum function at a variety of different unrolling factors. This is all computed automatically by this. I created a static IOTA function and I templated the unrolling factor. And here's one interesting thing is that we actually have numbers for 128-way unrolling. Can you imagine sitting there and implementing 128-way rolling manually? I bet nobody even knew until today what happens when you use 128-way unrolling, because it would be basically impossible to implement by any sane person in any other language. But anyhow, you see we basically have a U-shaped curve. We break a dependency chain when we move from an unrolling factor of 1 to 2. Gets a little better at 4, stays about flat until 32. And then things start getting worse. We probably start hitting instruction cache problems, or ending up with a huge stack of all the stuff that we had to spill from registers, or who knows why. But once we get up to 128, it gets a lot slower.
Standard parallelism, maybe?
Yeah, I was going to get into that on the next slide. So this motivates a few interesting things. First of all, standard.parallelism.reduce actually already implements these instruction level parallelism optimizations, because your reduction function has to be executable in parallel anyhow. And I actually, when I was making this presentation, I realized there's a bug in it. It requires commutativity in addition to associativity, but that's easy to fix. I'm going to fix that. And it motivates, why don't we have a standard.algorithm? This has been discussed before. I don't remember why it wasn't implemented. A standard.algorithm.unrolled reduce for associative reduction functions that takes advantage of instruction level parallelism. And the other thing that came to mind while I was making these slides was, why isn't in standard.parallelism and in the hypothetical standard.algorithm.unrolled reduce, why isn't the unrolling factor templated? It seems like a pretty useful thing to template that, so you can figure out for each individual reduction function by trial and error what the unrolling factor should actually be that leads to the most efficient performance. Of course, that would require static IOTA, but that's not hard to implement. And unfortunately, the benchmarks on this are done in GDC, because DMD is incapable of storing static array elements in CPU registers, even if they're only accessed by compile time known offsets. In theory, they should be treated like regular stack variables. In practice, they aren't. That's bug 9991.
So that's where that came from.
Yes. It came from me making these benchmarks, actually. I think I filed this like a week or two ago, and I think Walter just couldn't believe that someone filed a bug report on that. Okay, so conclusions. So D's unique mix of features, especially template metaprogramming features, leads to some design patterns that aren't common in other languages. Either aren't implementable at all, aren't implementable as easily, or aren't implementable as well. So, and a lot of these reduce code duplication in places where traditional object-oriented patterns fail and leave you with a big Java-style mess. And lastly, these metaprogramming capabilities suggest that we ought to be creating abstractions of these patterns in Phobos. For example, standard.algorithm.unrolled reduce, and maybe a standard.patterns module to automate away the boilerplate behind a lot of these design patterns and make them even easier to use. Questions?
Can you explain the difference between the reduce, which does already does unrolling, and the one you suggested in standard algorithm, unrolled reduce?
Parallel, standard.parallelism versus standard.
Yes.
Standard.parallelism.reduce uses thread level parallelism in addition to the instruction level parallelism that you get by unrolling. Standard.algorithm.unrolled reduce would not do this. It would just do it in a single thread but unrolled. Walter?
I think this is just super valuable stuff, and I'd like to see a set of web pages, you know, one page for each of these patterns put on the website.
Interesting.
What?
dtutor.org.
Start on it right there, yeah. This really needs to go on the website.
Did you have a question? Oh, great.
Yeah, we snatched that one. Questions? David, questions? All right, let's give David a hand. Thank you very much. We got like 10 minutes break.